This video is for lesson 2-2 about deductive reasoning. Learning goals are to use deductive reasoning to prove that a conjecture is true and to develop geometric and algebraic arguments based on deductive reasoning. In the previous lesson, we used inductive reasoning by looking at patterns and examples to make conjectures, but we found out that sometimes our conjectures weren't actually true. And so this shows us a problem with using inductive reasoning. It doesn't guarantee that a conjecture is true. In mathematics, there are certain methods and rules of argument that mathematicians use to convince someone that a conjecture is true, even for cases that extend beyond the observed data set. These rules are called rules of logical reasoning or rules of deductive reasoning. An argument that follows such rules is called a proof. A statement or conjecture that has been proven is called a theorem. In geometry class this year, we will prove that many theorems are true and then use those theorems to solve problems involving figures. Below are some definitions from arithmetic. Here's a reminder of what an even integer is. An integer that has a remainder of 0 when divided by 2. Examples are 2, 4, 6, 8, and so on. An odd integer is an integer that has a remainder of 1 when it's divided by 2. Examples are 1, 3, 5, 7, and so on. In the following items, you'll make some conjectures about the sums of even and odd integers. Question 1. Calculate the sum of some pairs of even integers. Show some examples and make a conjecture using these examples. So I chose some even numbers. 2 plus 4, that makes 6. 6 plus 8, that's 14. 10 plus 16, that's 26. Based on this limited set of examples, I think that the sum of even integers is an even integer. That's my conjecture using inductive reasoning. That is based on a set of examples. Number 2, calculate the sum of some pairs of odd integers. So here are some examples. 1 plus 1 is 2. 1 plus 3 is 4. 5 plus 9 is 14. From these examples, my conjecture is the sum of odd integers is an even integer. Number 3, let's calculate the sum of pairs of integers consisting of one even and one odd number. 1 plus 2 is 3, 3 plus 4 is 7, and 9 plus 10 is 19. In each case, I chose an odd number and added an even and discovered that the answer is odd. So my conjecture is that the sum of an odd and even number is an odd integer. The following items will help us write a convincing argument called a proof that supports those three conjectures. Figures A, B, C, and D are puzzle pieces. Each figure represents an integer determined by counting the square pieces in the figure. So figure A represents the integer 10. There are 10 squares. Figure B is the integer 6. Figure C is the integer 11. And figure D is the integer 13. Question A, which of the figures can be used to model an even integer? That would be figure A and figure B. Question B, which of the figures can be used to model an odd integer? That would be figures C and D. Question C, compare and contrast the models of the even and odd integers. When we look at the models of the even integers, notice that they consist of 2 rows of squares, and that in each row there are the same number of squares. The model for the odd integers, however, have 2 rows of squares, but there's an extra square attached each time. Number 5, which pairs of puzzle pieces can fit together to form rectangles? We could fit A and B together. A picture of that would look like this. Here are the 10 squares from A and the 6 squares from B. We could fit figure C and D together. Here are the 11 squares from C, and then the 13 squares from D. Number 6, explain how the figures used as puzzle pieces can be used to show that each of the conjectures were true. We could fit the pieces together. For example, if we fit the 2 pieces that represented even numbers together and found out that the answer was a puzzle piece representing an even number, then that's proof of our conjecture that an even number plus an even number equals an even number. In items 5 and 6, we proved our conjectures geometrically using the shapes. Now let's prove the same conjectures algebraically using symbols. This is an algebraic definition of an even integer. An integer is even if and only if it can be written in the form 2p, where p is representing some integer. We could use other variables instead of p. So number 7, use the expressions 2p and 2m to represent even integers and confirm the conjecture that the sum of even integers is even. So the word sum means to add, so let's add together our two integers, 2p plus 2m. Then using the distributive property, we can factor out the 2, creating 2 times the quantity p plus m. If you add p and m together, which were integers, that's going to create an integer. Let's call that n. So that means that we can rewrite the 2 times p plus m as 2n. And notice that again, this is the form of an even integer. So this series of algebra steps shows that when you add two even numbers at the beginning, and then do a little bit of algebraic manipulation, that you create an even number at the end. That is proof of that conjecture. This is an algebraic definition of an odd integer. An integer is odd if and only if it can be written in the form 2t plus 1, where t is an integer. Again, you don't have to use the variable t. So number 8, use expressions for odd integers to confirm the conjecture that the sum of odd integers is an even integer. So let's add together two odd integers. How about 2t plus 1? That can be our first odd integer. And let's add another odd integer, maybe 2p plus 1. When we add these together, we'll get 2t plus 2p plus 2. Factor out the greatest common factor of 2 to create this result. T plus p plus 1 will make an integer. Let's call that integer n. If we do that, then we can rewrite our 2 times t plus p plus 1 as 2 times n. And this has the form of an even number. So adding two odd numbers together, working a little bit of algebra, creates an even number at the end. That proves that conjecture. Number 9, use expressions for even and odd integers to confirm the conjecture that the sum of an even integer and an odd integer is an odd integer. So here we have an even number plus an odd number, did a little bit of algebra on it, and at the end, create the expression for an odd integer. In items 5 and 6, we developed a geometric puzzle piece argument to confirm conjectures. And then we did an algebraic argument. Even though one method is geometric and the other is algebraic, they're both often seen as the same argument. Number 10, explain the link between the two methods of proof. So one way to answer that would be like this. The algebraic expression 2m corresponds to that geometric model of having two rows with m squares. The expression 2p plus 1 corresponds to that geometric model of having two rows with p squares plus an extra square in one of the rows. So number 11, let's state the three theorems that we just proved. Here they are. The sum of two even numbers is even. The sum of two odd numbers is even. The sum of an odd and an even number is odd. Here are some check your understanding questions, so I'll pause the video so that you can work on these. Here are answers to the check your understanding. Number 12 is up here in the top corner of the video. Compare and contrast a theorem and conjecture. A theorem has been proved to be true. A conjecture is a best guess based on observations. Number 13, Todd knows that 3, 5, 7, 11, and 13 are prime numbers. Based on this evidence, he concludes that all prime numbers are odd. Is this an example of inductive or deductive reasoning? This is inductive reasoning. He's using those example numbers to base his conjecture on. Question B, is his conclusion correct? No, it's not, because 2, which is an even number, is a prime number. Number 14, Shayla knows that all rectangles have 4 right angles and that figure ABCD is a rectangle. She concludes that figure ABCD has 4 right angles. Question A, is this an example of inductive or deductive reasoning? It is deductive because she used that theorem to make her conclusion. The theorem was that all rectangles have 4 right angles. Question B, is her conclusion correct? Yes, it is. If all rectangles have 4 right angles, and she has a figure which is a rectangle, then it is logical to conclude that it has the 4 right angles. In this lesson, we started to discuss deductive reasoning to create proofs of conjectures. We used geometric and algebraic arguments in our deductive reasoning.